Hello, everybody. So today we will look at an alternative measure of alternative way of measuring correlation between the returns of two assets, asset X and asset Y. So last time we covered Pearson correlation coefficient, or a lot of times we just call it the correlation coefficient because Pearson is the most popular and the most common way to denote correlation. But it certainly is not the only one available to us in statistics. So, Spearman's rank correlation is another way. It's a type of an ordinal correlation measure, meaning that the magnitude of the observation is not as important. It's not important at all, but only the rank of the observation relative to all the other observations is what's important. So it's a robust statistic as we know it, so it's less sensitive to outliers than Pearson correlation coefficient. So let's start with denoting our returns. So return of x and return of y are the two variables that we will be working with, because remember, we're not interested in the values of the return of the assets, but rather the returns on these assets every year. So we'll use the same formula as before: ending market value divided by the beginning market value minus 1. The return of asset X during 2009 is 20%. The return of asset Y during that same year is 15%. If we drag down this formula um, all the way, we get our return. So these are our observations that we will be working with. So now we need to rank our returns. So if we rank the returns of asset X from smallest to largest, we can do it manually. So let me just denote my columns here: ranked return of X. Um, we know that the smallest value is negative 15%. The next smallest value is negative 10%, and so on and so forth. But for a sample this small, we can definitely do it manually. But I will still use a function in Excel called, well, actually, I will just copy these values into the ranked section, and I will paste them here, and then I will sort these values from smallest to largest. So now these are the same values as I have for the returns of X, but they're ordered, they're sorted from smallest to largest. Now we need to get an assigned return of Y corresponding to each one of these ranked returns of X. Let me label my column first, and then we'll see what is my assigned return of Y. To get the assigned return of Y, first I need to find out what year does this observation come from. The negative 15% happened during the year 2012. What is the assigned return of Y, meaning what was the return of Y during that same year? For convenience purposes, let me add another column for the year, and let me identify the year of each of these returns of X. So the negative 15% happened in year 2012. The negative 10% was achieved in year 2010. The 20% return was achieved in year 2009. The 75% return was achieved in year 2013. And finally, the 75.9% return was achieved in year 2011. So the assigned return of Y is the return of asset Y in the year 2012. So we know it's the 17.07%. Again, we can do this manually, or if this was a larger data set, we would definitely use some kind of an automation or a function. So let me use the function known as the VLOOKUP, which will help us do it a little bit faster. So we're looking up the value of 2012 in this table, and I am interested in the fifth column, with the exact match. So in 2012, my return of y was 17.07%, so my function helps me do that. In 2010, my return was 100%. In 2013, my return was negative 20.83%. So now we have ranked and assigned returns for the two variables. Now, the formula itself only cares about the rank and more specifically the difference in ranks. Before we can get to the difference in ranks, we need to compute the ranks of each of these returns. So rank of x and rank of y. So rank of x is the spot that this return takes in the array of ordered observations. We already pre-sorted them, so we know the ranks of x values are 1, 2, 3, 4, and 5. But again, let me use a function in Excel called rank of this number in the array of these 5 numbers in the in the ascending order. So negative 15.79% is the first smallest observation in this array of 5 values. So let me fix my formula here. Let me do it absolute reference. Now it works. Rank of y. So what is the rank of this observation in the array of these 5 numbers? So 1, 2, 3, 4. So the 17% is the fourth smallest return amongst these 4 returns. So if I use the same rank function of Excel of the 17% amongst these 5 numbers in the ascending order, Excel tells me that it's the fourth smallest observation amongst the 5. And if I drag down the formula, I will see that the first smallest or the smallest observation is the negative 20.8%. The largest observation is the 100%. Now that I have my ranks of x and y, I can compute my d. D is the difference in ranks. It's the rank of x minus the rank of y. So we get negative 3 as the difference in ranks between x and y. And we do the same thing for the other pairs. 2 minus 5 is negative 3. 3 minus 3, the difference is 0. So we have our list of differences. The formula says that we need to square those differences and then take the sum of the squared differences. So let's compute the squared differences first. It's the difference squared. So negative 3 squared, we get positive 9. And we copy down that formula. Now we have the d squared observations for all 5 years. Now we need to take the sum of the d squares. So let me denote it as sum of d squares, and I will use the Excel function to add up the 5 values of the d squares. So the sum is 36. So 36 will be used to plug in into the numerator of this formula. The denominator of the formula says n times n squared minus 1. N is the number of observations, the number of years, the number of paired observations. So it's 5 years, we know it, but to remind ourselves, let's just use the count formula and put it, oops, yes, it's 5. So now, before we plug in these two numbers into our formula, as I like to do, I will put the numerator and the denominator separately, and then we will use it to compute the numerator and the denominator respectively. So the numerator is 6 times the sum of these squares. So sum of these squares is 36. So it's 6 times the 36. The denominator is n times n squared minus 1, and we already know that n is equal to 5. So it's the 5 times 5 squared minus 1, which is 120. So now we're ready to compute our Spearman's rank correlation. Spearman's rho, so the Greek letter rho is used for the correlation coefficient. So Spearman's rho is 1 minus the numerator divided by the denominator. And we get a coefficient of negative 0.8. For reference purposes, let's recalculate our Spearman's or our Pearson's coefficient. Pearson rho using the correl function of Excel of the two arrays, which are the returns of x and y. So our Pearson's rho was negative 0.74, which was pretty strong. It was close to 1. It was a strong negative correlation between the two variables. Spearman's rho is interpreted very similarly. So it's a negative correlation, meaning that when asset X tends to go up, the other asset tends to go down, and vice versa. When Y goes up, asset X tends to go down, and it's a pretty strong relationship because the value is very close to 1. And both Spearman and Pearson's rho are very close to each other. The interpretation is similar, but again, the difference is that Spearman's rho, Spearman's rank correlation, is an ordinal measure, so it's not as sensitive to outliers as Pearson's correlation coefficient is.